Let's move then to the topic of filter design and automation. I think Alexandra has already done a great job in showing the various aspects that are available, but I would like to dig a bit deeper and talk a bit more in length about what we have available for designing filters. And I would like to start with just this overview of a typical filter development workflow, where you would typically start at the bottom of the spiral with the type of synthesis, which is your network, your circuit network that you are synthesizing in one or the other way to get a specific transfer function, a specific filtering characteristics, basically. And so this is the thing that we typically do as electronic engineers as well. And with this reference design, then you need to go and implement this in a 3D model, in a distributed model, because we're working at high frequencies. So this is where you can go and realize it in a 3D simulation model. And then, of course, inevitably, you need to optimize it and get the correct dimensions for this model as well to achieve this desired filter response. And there's always parasitic effects, there's always dispersive effects that also needs to be taken into account in this step, as nothing is as simple as just a circuit. Now, we have then tools also to cover, of course, the preparation for fabrication. So basically your CAD modeling with all the details in it. This is, of course, where SolidWorks, one of Dassault Systems' CAD tools, are very useful for modeling these complex structures, and even being able to import that back into CSD fully parameterized and do a final optimization. This is possible. And then finally, we end up with the assistive tuning, where even there we do provide some solutions with our software. And I will touch on each of these aspects and show you some examples. Yeah, but most of this is centered around our tool called Filter Designer 3D, as already introduced in the previous session. And I think it's appropriate that we actually do a little demo of the software environment, so you can see for yourself how things look like. And so let's get started. Here we basically have Filter Designer 3D, the backstage, the starting page, where you can select different responses. So you will see there at the top, we can select between low pass, the band pass, and even diplexers in the end. And one can also find a couple of different example templates here. This is a good starting point if you are new in FD3D, and you can see that some contain synthesized networks, while others, full models with various implementations. You see the planar stuff here, there's cavities, and even some diplexers as well. Now, let's get started by just selecting a low-pass filter response. And then the first thing existing users may notice is that we now also have circuits in FD3D. Let's increase the order here and maybe add some transmission zeros and move them around. And so you can see there then the circuit on the right-hand side with the element values. And if you go to the filter circuit tab now, you can quickly also select more topologies or just create the schematic. And it opens Design Studio, the circuit environment in CSD, where you can add interconnects or play around with the optimizer task that's already set up there for you. So everything's pre-configured and you can take this further. Okay, next I would like to go back and start with the bandpass filter. And now you will find that we have the coupling matrix representation by default, of course. And now let's take a look at the transmission zeros that can be added here. In addition to the normal zeros, there's also the symmetric pairs for more practical realizations, and then also complex pairs for group delay equalization. So, but in this case, we're just adding some normal zeros, and we want to next go and take a look at the topologies as well. So we switch to the coupling matrix tab, and there you will find the typical tuplets. So cascaded triplets, quadruplet sections, and there's special implementations for dual mode resonators and also folded boxes. And then we have also added more topologies like resonant couplings, non-resonating nodes, these dangling resonators, and even a mix of these. So it's really a whole lot of different topologies. So we select this one and go ahead and yeah, you can also interact, of course, with the coupling matrix, changing some values. You can see how these elements affect the response in the end. And there's a couple of nice things to play around with. And the point is, it's very fast and responsive, this interface. But let's maybe get back to the slides again and briefly before I continue to another demo. So I would just like to introduce then first the modeling concept that we are also using. So you've seen the synthesis side of things with ladder circuits and coupling matrices. Now, if we talk about bandpass filters, we are typically referring to coupled resonators, which consist of many similar components. You can see it breaking up into the various resonators, the inductive couplings, the capacitive couplings, the port couplings. This is also true for ladder circuits. But let's go along with the bandpass example. And our workflow starts with a specification, selecting the topology. We've discussed that just now or showed that in the demo. And then you can do a layout. And basically for each of these components, you select the models you want, and you can go and design these equivalent components. And in the end, FT3D builds the model for you according to your layout, and it executes a space mapping routine to optimize the response as well. And finally, it even provides you the assistive hardware tuning based on your synthesis. So let's maybe get back to the demonstration. And in this case, I would like to start with this response and pre-selected topology. And then we go and we select, you can just see, yeah, we select from a list of technologies here, where you can see different cavity configurations as well as planar technologies with typical resonator realizations there, SIW, hairpins, things like that. But we select the coupled resonator option, which is basically the general solution for any cross-coupled cavity filter. Okay, then we get this 2D representation where the layout can be changed. In this case, we want to make the overall footprint smaller, so we rearrange it. And then we can go and select the inductive coupling here and enter the component library. This is where I can select any component there for this inductive coupling. So I select this iris with a ridge inside just for stronger coupling in this case. You can select your own components there as well, load your own components. And you can see then the parameter list here. What I want to do is just assign this ridge height for the design as a design parameter, and you can also see the range for the design space there as well. Next, I just want to switch through different components so you can see how the parameter list updates. And then we've introduced this new thing here, which is the design assistant for the default coax resonators in order to dimension it with based on frequency, mode suppression, Q values, and so forth. Okay. We are now all set and ready to start the eigenmode analysis. And here you can see basically a bunch of processes being queued. And if we switch to CST Studio Suite, you will see the simulation project that's created in the background for the resonator, and where the insertion of the screw is just buried. And you can see then the results for that as well. And then once that's done, you see all the other couplings being built, all these other components. And as they finish, the coupling matrix starts turning green, and you can go and view the corresponding design curves, basically the normalized coupling values as a function of the design parameter. And then you select model creation, and it quickly builds this model. It assembles all these different components in CST Studio Suite, and you see the assembled model here according to the topology layout. and you can switch to the simulation project where you can view the mesh and results. After this is then finished, see the final results here. And if we maybe just step back to FT3D, we can also go and analyze the results of each of these optimization iterations. We can extract the coupling matrix, as you see here, and just see how the errors basically decrease as we reach convergence. And at the right-hand bottom, you can see the convergence curve. So that is quite a mouthful. And the one thing that we did not discuss necessarily here is the space mapping. So this is an automatic routine that kicks in when you create the model, which utilizes basically the eigenmode results and the coupling matrix extraction to efficiently optimize your model. So basically here you can see a range of more complicated models. I mean, the one we already discussed in the right-hand corner, but there's also a diplexer example. You can see the substrate integrated waveguide filter, as well as a split ring resonator filter that's even implemented in stripline technology. Now, what you'll notice here, it's not just the very nice tuned up responses with perfect equal ripples. If you notice the dashed lines, these are actually the return losses for each of these models when the initial dimensions are used from the eigenmode analysis. Of course, they are detuned because all these different components, when you are solving them in isolation, you get a different picture. When you bring everything together, of course, there's loading effects that was not possible to be taken into account, and it detunes the response completely. So we start from this dashed line, which is sort of total reflection in some cases, and you can just see the convergence curves here then for the various examples. What is remarkable is even for the worst case scenario, which is the diplexer, you expect this to take longer. It's in less than 15 full wave iterations that you go from completely detuned response to something that is almost perfect. So yes, let's just take a look at that and just embrace this really remarkable results that we are getting here. And we see this consistently. If you go through all our examples that we have in these templates that we have in FT3D, you will see similar results. Okay, let's step on and say that, look, I have a complicated model. It might be a multi-mode model. I cannot build this with this workflow in FT3D. Of course, you can go and model it by yourself in the 3D environment of CST Studio Suite. And then we have a specialized filter optimization for that. And the idea is that you're not using S-parameter masks here. No, you're actually importing your FT3D project, which contains the synthesis. So basically, this then serves as a surrogate, whether it's the coupling matrix for the bandpass filters, diplexer filters, or it is the ladder circuits for the low pass or the high pass filters. The optimizer makes use of these surrogates and tries to minimize the extracted errors. And the point is that this is a very efficient approach. And we have even introduced or enhanced the parasitic extraction and parasitic and dispersive handling with some new technology in FT3D, which is worth mentioning because we have also a patent pending on this. So this is also even more enhanced in version 2024, which I would recommend also to go and try out for these low pass or high pass filters. Okay, now talking about optimization, the trust region framework algorithm is one that we typically utilize for the filter optimization. The nice thing of this gradient-based optimization is that one can utilize sensitivity results. Okay, and this greatly speeds up the optimization. So here is just an example of a multi-mode filter, and you can see there the response. It's 1% fractional bandwidth, so really a sensitive model. And you know, you just sneeze at this thing and it is detuned. So the point is, we are able to optimize this as well, making use of this approach that I just showed you. And more than that, then the TRF or the Trust Region Framework utilizes the sensitivities, and you can see, even under 10 iterations, actually, you already have convergence. This may vary depending on the complexity. But the point is, if you look at the finite difference convergence curve, which is in blue, you see 2 steps until it reaches convergence. And that's just because, the derivatives are calculated, which is not needed when you already have them by the sensitivity analysis. And maybe it's also worth mentioning for the old CST users that you don't need to set up constraints, phase constraints in your models. You can also just utilize normal geometrical parameters for the sensitivity. Okay, let's take a look at different filter examples. We have talked a lot about cavity models, but of course we also support various planar filters in both microstrip or stripline. We introduced this a couple of versions ago already. You'll see things like split ring resonators, folded rings, which you can really play with in terms of placing transmission zeros and having more topologies and not just the inline style topologies. You'll see the hairpins, the interdigital with quarter wavelength, of course, transmission lines, and then also edge coupled filters. Another thing that we have introduced, because we are synthesizing and able to extract ladder circuits and the equivalent components, is that you are actually able to apply the same workflow that we do for bandpass filters for ladder circuits, where you can implement the equivalent inductors or capacitors with your distributed models. And we utilize the partial RLC solver for that to get the partial L or C value. And you can see the design curves there quickly, and it builds the model for you. And again, it optimizes it for you. And within 5 full wave iterations, you can see very nice convergence for this low pass filter. Now, really any component can be used that is equivalent to the L or the C. Here you can see a shunt capacitor in the form of a Christmas tree. So, and the measured results look pretty good. So this was some fun that one of our developers had during Christmas time. But again, you can be quite creative, and all of this automation allows you then to explore new things without the tedious task of space mapping and building models and things like that. Of course, we talked about ladder circuits, but normal stepped impedance synthesis can also be utilized, for example, with a coax low-pass filter. Here you can see that, where again, you can go and load your own components in the library and stitch them up with this assembly approach that FT3D uses. I mean, FT3D does this for you. For example, realizing the capacitance here or the high impedance or the low impedance lines might be difficult, so you can load your own sort of implementations for those. And let's say you have more exotic resonators you want to be using, like this one shaping out here, which I will present later on the shape optimization. You load this model, this component, along with the other components you'd like to use, and quickly it builds this model for you. You get the response optimized, and you can just see the nice equal ripple after basically 3 full wave iterations. Now, if we move on to waveguides and specifically non-resonating nodes, which is a new synthesis or topology that we do. We introduced non-resonating nodes in the coupling matrix, which we didn't have before, so this is new in 2024. The idea is that basically these dangling resonators attached to these non-resonating nodes, which is depicted here in the picture, are realizing these transmission zeros respectively. So basically, this then allows you to work with inline topologies and have these dangling resonators and quickly introduce transmission zeros without cross couplings. For example, in a waveguide filter, it's quite difficult to realize cross couplings, or it is less practical depending on what you are trying to achieve. And so you can just, you know, have these dangling resonators, and you see again, this can be built with FT3D and optimized, and it takes a bit longer in this case. But if you look at the gray curve there in the background, that was the initial response. And you can see even a transmission zero right in the center of the passband. So really detuned, and it's able to just find a fully converged equal ripple response. I think what is important here also just to understand sort of from a practical aspect is that you have susceptance values, specific susceptance values that you need to implement. So for example, talking about a positive susceptance, which realizes typically the low side transmission zero, you know, you need to hit the right length of the wavelength between the first and the second order mode, and vice versa, or well, not vice versa, but actually for the high side, basically it's again between the second and the third mode to get you know, the appropriate susceptance value. And yeah, more details on this will be shared later in the application note as well. But we support this now in FT3D 2024 as well. Then another interesting topology we introduced in 2024 is this what's called a resonant coupling. So between resonator 2 and 3, and this is also again introducing a transmission zero. So the resonant value that you achieve there with this coupling introduces the transmission zero, and here you can just see then the realization of that, where we have like an equivalent series resonator with a capacitor and an inductor realized there. So this is also in the component library that you can play with if interested. And yeah, then there's also the diplexers. So as mentioned before, we do also support diplexer synthesis, coupling matrix synthesis. We support star junctions as well as common resonant junctions. So in this case, we are able to build diplexers with resonant junctions. We don't have a component yet for the star junctions, but nevertheless, this whole workflow can be applied in this case, and you can see this model. Let me just see why this is not moving now. You know, you can see these tasks created per channel, so you can actually optimize each of these in isolation if needed, if it's a bit too tough, and then do the final optimization, or just everything together. This is quite a simple one, and we're able to get a good response there. Now, talking about things that may be tough to optimize, we get to multiplexers. This is quite an interesting topic because, you know, there's different ways of realizing multiplexers. Probably one of the most common approaches are the manifold coupled multiplexers, as they enable, you know, compact and low loss design, you know, as opposed to something using circulators or things. Yeah, but however, the design itself and the optimization of such a multiplexer is quite difficult and can be extremely time consuming. So what we did was we came up with this new workflow based on all the building blocks that we already have and enhanced for this. And so the workflow is similar to what I showed before, where you start with your specifications for your channel filter. You select the topologies you want, you get to the optimized isolated filter, and then you repeat that for each channel, and you basically build these models into a single project. There's an option in FT3D for that, where you say build into you know, existing or open project, and it's able to do that, and you know, with the correct parameter mapping and things. And then basically, yeah, we just go on. You need to go on and then build your own or design your own manifold. Implement that. Can be in the schematic environment. It can also be in 3D or to assemble things. And then what you want to do is you want to apply a piecewise optimization approach. So this is based on a workflow that's already well known, I think, from Cameron's filter handbook, I think, which many of you may be familiar with. So we basically utilize that, and we do a channel by channel extraction. So the difference is here that we are doing coupling matrix extraction, and we are utilizing a 2-port coupling matrix for each channel. And so you would be going finally through every channel while everything is connected, starting with the manifold first, then third channel, second channel, first channel, as you can see there. And then finally, when you're happy, you go on to the complete model, which you already have the complete model, but I mean, with the optimizer set to have, in this case, 3 different goals for the 3 channels, and you select, your manifold and a few of the initial or the parameters closest to the manifold in the filters, and you basically optimize all of this. We have an application note that will soon be published as well in the knowledge base on this, and you can get more details about our proposed workflow. Okay, coming to assistive tuning then. This is then the final topic, and so all of this extraction things we can also apply to your device under test. You have used the FT3D environment and to design. Now you want to use it also to go and tune up your filter that is on the bench. And so you have your network analyzer set up with the measurements. You connect it to your machine where CST is installed and FT3D is available. And basically, FT3D reads directly the S parameters coming from your network analyzer, and real time does the coupling matrix extraction. And you get these error bars at the bottom of FT3D where according to the couplings and self-resonances, how far they are detuned, which screws to go and tune, and you can map this out for someone that's also working in the lab and tuning this for you. And it also has a Python API if you are interested in automating all of this. So here you can just see an example, and you can also see how well it compares with measurement. Now, what is important is, I talked about the multiplexer workflow just before. In a similar fashion, you can tune up your multiplexer using that approach as well, doing channel by channel extraction, essentially, and just trying to get this time-consuming process down. And you could even use the API to automate things. So just be aware of this. It is all available and there to go and try out. So this brings me to the end, and I would just quickly like to summarize a few highlights of FT3D. We have, the coupling matrix and ladder circuit syntheses. So you can do a quick, synthesis of a large range of useful topologies. S parameters based extraction of the equivalent networks can provide insight into the geometries. You don't need to go and place ports inside your model and determine the coupling values. You can use this extraction method, the assembling modeling is very useful, as it is fast and robust, and you can make use of your own customized models that you load into our library, and with the right tags you have access to that. And then there's the automatic parameter mapping that we provide, creating simulation projects for you. So all of this is done with FT3D. And then there's a range of things with the optimizers, efficient surrogates for the filter responses. It's capable of utilizing sensitivities for fast optimization. I showed you the robust space mapping routine we have, and then even capability of multiplexer channel extraction. And finally, there's the computer-aided filter tuning for real-time systems, and having the same environment for the virtual as well as the physical bench. So that is the end of my talk.